Okay, so yeah, looks like a low turnout today. I got a cold, so I got this mask to try to prevent the spread of this thing, which is it's kind of mild, but it's lingering, you know. So anyway, so that's so the recording, did that go okay? Or I don't know. I didn't get any questions or anything from it, so I guess it was all right. Then anyway, so then a couple of you emailed me about the homework, like I was flying, you know, so I couldn't answer. And like by the time I got home, like I couldn't do it. So anyway, sorry about that. I guess yeah, anyway, that's how it worked out for that. But anyway, so yeah, so last time on the tape I went through like intrinsic viscosity. Um, Basically you kind of end up with this equation that the intrinsic is going to go with mass to some power and then a prefactor. So those are called the Mark-Hoek coefficients. And you can look them up in the Polymer handbook. That's the main source for those. So you can look up every polymer in the Polymer handbook, but those coefficients will change with the temperature, the solvent, and the temperature. So there'll be like different numbers for solvent temperature. And the classic, like for Gaussian theta solvent, this will be a half, and for the power will be 1/2. And for good solvent, it's 0.8. And if it's a rod, like you can have tobacco mosaic virus, some other kind of colloid or polyelectrolytes, and this goes to 2. You get a steeper dependence. But if you look in the handbook, I didn't have a copy of the Polymer handbook, I guess, online, so I have a hard copy, but anyway, I didn't put it in here, but basically the number doesn't exactly, this power, Mark-Hoek coefficient, so it's called A and there's a K in front. So the A coefficient doesn't exactly follow those rules. Like if you look, it ranges all over the place, you know, so it doesn't exactly follow this theoretical rule for that. Okay. So anyway, so there's that business. So I think you guys have seen Mark-Hoek coefficient before, I think. I mean, most of you probably, because it's in intro to polymers and stuff. And then, all right, so the other case is if it's 3D. So if you have just 3D, then that's 1 minus 1 is 0. So there's no dependence on molecular weight if it's 3D, right? So okay, that's important because and if it's 3D, if it's spheres, then you get this equation, which is the Einstein equation for viscosity. And you'll see like modulus, storage modulus, the storage modulus times volume fraction times 2.5. That's used in composites. And then the Guth-Gold equation is like they add a squared term to this. So it's 2.5 here, and it's like 15 times phi squared for modulus. So whenever you have like composites, so this is just a displacement law, so you can use it for anything, any kind of property. You want to just say, well, you're removing some of the material by putting this stuff in, that volume fraction of stuff, and that shifts the property, the constitutive parameter. So anyway, so I went through that stuff. Temperature dependence is Arrhenius, and you can match up the WLF equation with just saying that it's enthalpy and entropy, and then a Vogel temperature. But then these C1 and C2, which are kind of meaningless, gain meaning because then you can say, well, C1 times TR is the enthalpy of activation for the viscosity. And then there's some ordering process going on in the flow, and that's this entropy term, right? So the entropy term, let's see, equates to somewhere. C2 is related to the Vogel temperature. SA, I guess SA, SA is just a constant, I guess. No, SA is 2.3 times C1. 2.3 relates natural log to log base 10. The C1 is actually the entropy. It's like C1 here is the entropic part of the activation energy for, in other words, this ordering going on when flow happens. So anyway, so that's kind of, that's why I have the mask. I have this cough. Periodically, I'll have like cycles of this virus, and I'll start coughing and get feverish or something or other. And then I'm fine the rest of the time. Totally fine, as far as I can tell. But anyway, so Simha's a guy that's kind of famous, and I think he's dead. He lived to like 110. And he was still teaching at 110 in case. So you'd go up there, and there'd be this old guy, like older than me, like really old. Then he'd be like hanging out there. But he did a lot of work with this intrinsic viscosity stuff, and he's pretty famous. Anyway, I thought I'd mention him. There's a book he has on that. I don't know if I mention it here, but let's see what this is. I don't remember what that is. Contacting the server for information. I guess this might be a obituary. So I guess he died in 2008, but blah, 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 blah. Anyway, yeah, Alex Jamieson took over he's kind of a dynamic light scattering person, I guess. So they're all pretty good people, so anyway, so that said, shear rate, we know about shear thinning, and it happens in solution too. And then you can have this problem that if you have a polymer that has shear thinning and you're using capillary viscometry, like this guy, that thing, so then you can be in a case where you're in the shear thinning region and not know it. That can be a problem. So it's good to be able to vary the shear rate so you can see if it's flat or not, which you can do in like a cup and bob viscometer, Couette viscometer, they call it, or you can do it with a cone and plate. Cone and plate's harder to use for solutions because it has to be a meniscus between the two things, and apparently that's harder with a cone and plate or plate and plate. Anyway, so branching is something they do with this intrinsic viscosity. So branching is kind of hard to characterize. So this thing is kind of funny, what they describe here, because high density polyethylene is usually described as long chain branching. So the other thing, so like high density polyethylene. Oh, sorry. It's .cam. Let's see, it should have worked. Maybe it's not going to work today. That's this thing. That might work. Is it just thinking about it, or is this thing not on? It says on. On. A lot of cables here, it makes me think that something might be. What goes down there? Is it just for computer? This guy looks like he belongs in this. Video out. Okay, that guy should have gone in here. This room seems to get a lot of action. Maybe that works. I don't know if that does anything. Oops, sorry, Ken. Communication. Video out 1. The video out 2. It should be perfect. It looks like I can do, I think. Anyway, I can do it up here. So high density polyethylene. So that's called a long chain branch. And low density polyethylene, which is the original polyethylene, which they took, basically you take ethylene monomer and you put it to 80 megapascal, so 800 atmospheres. So it's supercritical fluid. And then you throw in some like AIBN, which will break apart into free radicals. And then that attacks and just makes a kind of a polyethylene snowstorm inside a supercritical fluid at 80 megapascal and maybe 100 C or something, 120 C, I think. Anyway, so when you do that, you get this kind of, I call it arboreal. You get a structure, kind of, it's like a shotgun structure. You get a lot of branching, branch on branch structure. And that's like a really cheap polyethylene, like the worst kind of, like you can stretch it easily. It's easy to process, but basically it makes something that isn't very nice. It's like really cheap film, like when you like they wrap wood or something with plastic sheet, that's this stuff. And then a milk jug is this stuff. So they're different kind of materials. Then there's like linear low density polyethylene, which is polyethylene. It's got a lot of short chain branches in it. It keeps it from crystallizing. So it's low density. Low density means low crystallinity. Linear means it's not this thing. Right. So that's a higher tech. So that's kind of number one. This is number two. This is number three in the order of pecking order of polyethylenes. There's metallocene polyethylene. You can have kind of controlled structure. I'm not sure how to draw it, but so it's got more controlled structures than linear low density. Anyway, they have this plot. So they say high density polyethylene, and they say long chain branched high density. So for linear polyethylene, high density polyethylene, high density isn't really linear. It's got long chain branches in it. They say high density, then they say long chain branch polyethylene, they call it low density. So that's not really true. Like that's not what they are. Anyway, so this high density shows a nice behavior of viscosity molecular weight. So the slope of that is the Markovitch coefficient. That's a log plot, so the slope is the power, right? And then the intercept's going to give you the K. So K and A from Markovitch. That's normal behavior. Low density, which is, I think, really like this stuff, not long chain branch. It's like an explosion, right? So that goes up. It's tooling up. Like, yeah, it's kind of linear when you have a low amount of it. But then when you get to it goes flat, right? So what's that? So basically, if it's flat, that means DF is 3 because it means there's no molecular weight dependence. When you have a 3D object, right? So that means your thing is acting like a colloid. It's not acting like a polymer. It's acting like a sphere, solid sphere, right? So as you go up in molecular weight, you transition from a polymer like with a small a coefficient. So small a means that DF is big, I guess. Right, so DF, say 2.5, that would be a randomly branched polymer. And then that would give you 3 by 2.5 would be 6 over 5, or 12 over 10. So minus 12 over 12, or 10 over 10 would give you 2/10, or 1/5. So 0.2, that'd be like a 0.2 slope. Yeah.
What's the difference between branch?
Dendrimer is this. The dendrimer is a controlled structure. We have, like, say, it could be tri or 4 tetra or penta or some other thing. And you're going to have these little molecules that can bond, so it'll attack on that and just make this. So it'd be like generation 1, generation 2, so G2, G3. I guess that's generation 0. So as you're going up, this is what you're doing. So these are used as kind of, sometimes as additives, sometimes as adhesives are made out of acrylics, polymers made of this stuff. So like DSM kind of had product lines along this approach. They're kind of fun molecules to look at. The question is, what is that? Is that a colloid or is that a polymer? You know, so, and basically, if it's small, it acts kind of like a polymer. So this is like generation 0, 1, 2, 3, 4, 5, 6, 7 for this kind of setup, right? Well, I don't know exactly. Oh, this is some kind of oddball 3,5-dioxybenzylidene It's got an aromatic ring with substituents in 3,5 position, I guess. I don't see exactly how you get a trifunctional, but anyway, so in tetra THF at 30. So it's kind of polymer for the first 2 generations, like boom, boom, and then all of a sudden it goes flat. That's a 3D object, right? And then it drops. The dropping isn't in the scheme. Like there's no scheme where you increase molecular weight. I mean, DF has a maximum of 3 in 3D space. Basically, that can't go negative. So what's that? That's kind of like this. So this thing is really the volume of the molecule over the mass, right? So the volume is dropping faster than what it should. And so that's kind of it only happens if the thing is collapsing, like it's collapsing on itself and getting smaller. As you increase the molecular weight, it becomes less miscible and it collapses on itself and makes a smaller and smaller object, I guess. That's my explanation, but maybe it's true. Anyway, so that could explain it. So flat, you can explain it's a colloid. That's like a colloidal sphere. And then this collapse thing is something else that's going on. So you can see this stupid little measurement where you stick the thing in the capillary thing. This was why Simha got so excited about it. You can tell like this is like nanoscale. It's like a nanoscale microscope with a little tube on your desk. So it's kind of interesting. Again, it's a lot of interpretation that goes into it, but it's kind of interesting you can do that. The chemists love this because they like simple things, they like to cook stuff and then like put it in the thing. So every chemist has like 10 of these in a drawer somewhere, and then a setup to keep it at constant temperature because they're always making different stuff. They say, what's the intrinsic viscosity? And if they know what the composition is, so if you know one, so if you look up in the handbook, you have the intrinsic and then you have A and K. If you measure the intrinsic, then you can get the molecular weight from it directly. So you can kind of use one calibration standard in this machine, and then you can get all the others. So if you have one monodispersed linear chain of whatever goo it is, polystyrene, then you could have any kind of branch structure or whatever. You can still get the molecular weight of it. Right. So anyway, so that's why people like that. That's why they teach it, because it's anyway. Yeah. Oh,
Which is not the Zim model. So
yeah. There's the Zim and the Rouse model. So the Zim model is the coil. Oh, this that projector was like that. Oh. I probably have to reboot the class to get it to run. So the Zim, you have the chain, and you just say that it's a sphere. Like I have the end-to-end distance, right? R whatever. And then I'm gonna like cube it 4/3 pi. That's the hydrodynamic volume of the thing. That's kind of like the size of that sphere. The Rouse model, I'm taking it like a bunch of train cars. And then every time I add a train car to it, the viscosity goes up. It's kind of like looking at the individual thing. So this is really non-draining. This is how the guy Heimitz. There's a couple of Heimitz books linked on the webpage, but he describes this as non-draining. Like he has a chapter non-draining, draining. So I think he kind of invented that. And this is Heimitz never really published papers, so it's kind of funny, but he wrote this like textbook that kind of copied a guy named Tanford wrote a biopolymer textbook. Kind of took that book and a little bit of Florey's book and he put them together with his own ideas. It's a really nice book. It's called Polymer Chemistry. And it was published in like 1980 or something. And then there was a second edition that came out that another guy wrote some of it and he jammed a lot more stuff in it. It's not as good as the first edition. It's kind of funny. Like the improvements made it worse, so, but anyway, Heimitz was not really an acclaimed guy and he just kind of wrote this book. It was a really good book. And then, anyway, so he was using these words draining and non-draining to talk about this. It's kind of like two models, little limiting models. So there's also, you're gonna have to basically include hydrodynamic interactions to account for where you are between those two. in terms of this viscosity thing. Right,
For high generation.
right. So that means the only way to get that is if the volume drops, so if it collapses. So you have it shrinks, yeah. Just put more chains into it, it gets smaller because the miscibility drops. That's what I say. I don't know why, but basically that's what I think. Like you can see these things get pretty complicated. So, and also, it doesn't look like it would be very like soluble the way it's set up. I mean, anyway, I think that probably the more generations you put in, at some point it just collapses down. Anyway, so there is a lot of interest because this can be like a drug delivery. So you can put like there's holes in it and you can pack it with stuff and then eat it. And then somewhere in your stomach, it'll release the stuff. Maybe you could also put things like polyethylene oxide on it that collapse at a certain temperature. So you could have it go to like a hot part where there's cancer or something or some disease, or you have a cold, and it could release right at the cells where the virus is like making me sick. And then maybe you could have a better cold medicine. Or it could kill you, I mean, this kind of thing, who knows what it does to you. But basically, that's along the lines of this drug delivery stuff. Every time they make a new molecule, they say, oh, it could be used for drug delivery. Because that seems to be like the go-to thing. Maybe it would have some use. Hard to tell. I'm not sure there are dendrimer drug delivery things. So the structure of this was studied by these two guys, Dowd and Cotton, French. So there's a Dowd and Cotton model for this thing. D-A-O-U-D, Cotton. They're both French, even though Cotton's an English name. And then they had the idea like the chain goes out. So the chain gets less dense as it goes out from one of these things. So out here, it's like good solvent, and then here it's theta solvent, and somewhere in here, it's like stuck linear chains, So they had a model where you could they plot the density of these things as a function of distance from the center. And it's like dense in the middle, and then it gets to this theta part, and then it gets to the other good solvent part, something like that. So there's kind of a theory that goes with it. It's a little bit of a naive theory, but it's popular. Anyway, so we got this other way to look at these kind of branch things, this fractal model that I went through before. So how do you, I mean, since this is like fractal dimension, you'd think that this would work. So this is how you describe topology. And DF just gives you density, right? DF doesn't have anything about what the thing is, just how dense it is. That's why a plate is two-dimensional, Polymer chains are two-dimensional. So you spin them around in space, they have the same density, right? So if this thing only depends on density, the density dimension, that means there's no information in this at all about really the topology. It's only saying like comparing the density. So that you should keep in mind with this intrinsic viscosity, because people do this. I'm going to say like, I'm going to measure the intrinsic viscosity of a branched and a linear chain. So I'm going to have the same molecular weight, two chains, one's branched, one's linear. I'm going to take the square of those, so NL squared to the 2 more or less. I'm going to give this G factor, and that's going to tell me something about the topology, right? So I'm going to use the intrinsic viscosity ratio to get that. So you can see, like, if the intrinsic viscosity doesn't depend on topology, you can't exactly get topology from the intrinsic viscosity, right? Because the information isn't there. Nonetheless, so F is the number of branches, the functionality. So those equations that relate G to F, like even though like that information isn't in DF, you need to know either D min or C to get the branching topic open, right? So yeah.
What else?
is 0.58 bonds counter.
Yeah, that's a constant that was derived like from experiment. That's from experiments, like to just empirical. So anyway, so this is popular. Like when people talk about branch polymers and they say they're going to get the intrinsic viscosity and get this G factor, are they going to get the G from some other way, like from radius of gyration? So anyway, so if you look at this, kind of what that thing is, if we have this equation, molecular weight to the 3 by df minus 1, then you're going to get this equation that Z would be the molecular weight. This is squared, so it's 2, and it's 3 by df. The minus 1 disappears for the branch, minus 3 by df to the linear, which doesn't have any topology in it. It's just the density difference between the two. So anyway, so you can calculate that G from numbers like the topology numbers, but you're not using the topology to get it. You're only using the fractal dimension. So I just mentioned that. You might see this G factor in a paper. I've had it in a homework before. So this is basically the go-to thing when you have branched and linear chains. I mean, people will get this G factor. What else? So polyelectrolytes are nasty for this because so you're typically going to get the intrinsic. So you're gonna plot the specific viscosity by concentration and extrapolate to 0 the intercept of the intrinsic viscosity. And if like here's the linear chain that's behaving normally. The specific by concentration extrapolates down. When you go to 0 concentration, that's the intrinsic right there. But if it's a polyelectrolyte, there's a lot of games going on. Like the chain itself has counterions. So as you increase the counterions, then you screen the charges. You get to by screening of the charges. So it becomes like a normal polymer after you get to a higher concentration. Right. So it's like you could say, well, when you have a high concentration of a polyelectrolyte, then I have a normal polymer. So if I extrapolated that down, I could get an intrinsic viscosity from uncharged. But then because you have charging on it, you get pretty weird behavior. It can go up or it can go down, depending on kind of what's going on. So people have studied that. This is what Colby is a guy at Penn State. He's a pretty good guy. He's done a lot of work, various areas. One is in polyelectrolytes. Anyway, so this is showing his scheme of what's going on here. So there's an overlap concentration for the chain. So he's got the linear part, and extrapolated down would give him the intrinsic. Then he sees a change in slope when he's above the overlap but below the entanglement, which is a big gap in it, I guess, for polyelectrolytes. Like in normal, there's a small gap, but here's a big gap in concentration between the two. Then he gets the entanglement molecular weight, and it takes off. And then C star star is what he calls electrostatic blob overlap. So Colby kind of worked with Witten he's at Penn State, but he worked at he was at what is it, in Rochester, New York, Kodak or something before, and then he went to Penn State. But then he also worked with Exxon and whatever it is, Annandale, New Jersey. And then he also, because he was there, he worked with the Gens in France too. So he's kind of been around. Anyway, so blob is a French idea, right? So the idea is that like there's a region within the chain where you have electrostatic interactions, and then at longer distances you don't because of the screening. So that creates a region where you have the scaling transition between these local things and the far apart things. And that region where you have the scaling, where you have the electrostatic interactions, he calls a blob. It's like and then you can make the chain into a connection of a bunch of blobs that don't have electrostatic, so they're just normal polymer. And so C star star is the blob concentration within the blob. You can see the story gets pretty complicated. We don't need to know the details really, but basically he goes back to like a normal polymer out here, more or less. So it should be like 3.2 or something, but I think it gets 3.5 for that. So you can see like it's limited data set. Like all right, so this is like, I saw a paper in biology, they say like the leave a point out method, which I kind of naturally used, but I didn't know it was actually a method, but basically you want to look at a data set like this, you glance at it, oh yeah, there's like 4 power laws there. Okay, so how many decades is a power law that you can believe? Like it has to be at least 1 decade. So this one's kind of half a decade in X and a decade in Y, so it could be believable. Then you do the leave the point out method. Like if I get rid of that point, do I still have a power law? Like I have 3 points with a line through it. So this whole thing is a little questionable. He has a theory that predicts it, but anyway. This is believable. I guess this is believable. And then up here, it starts to get a little weird. So anyway, it's the best that you could do probably, but you know. So so he's got this is P2VP 17% cortinized, means he's ionized 17% of the chain to make it a polyelectrolyte. There's got this is another Coulter thing. You see he's done a lot of work. So he's got the same, I think this is the same polymer, poly-2 vinyl pyridine. It's got a amine group in it. And then one of them is neutral. He hasn't been cortinized. It hasn't been charged. And the other one is cortinized. So he's got a comparison between so the red one, I think, is let's see, blue, 55% cortinized is blue, and neutral is red. So red shows power 1. I mean, you normally just say it's power 1. So it's like Rouse behavior up to here, and then it gets entangled and it goes to 3.2. I mean, he would say like, I have 1 slope here, 1 slope there, another slope here, and another slope there. So, I mean, he's probably right. He's pretty smart. But basically, I would say it's 1 slope and another slope, and let's leave it at that because it's nitpicky kind of to go after these other things. But and then when he has the polyelectrolyte, so he charges it, then he gets quite a bit different behavior. He has the power 1, and then there's like overlap of the ion concentration, and finally it becomes linear when he gets to high concentration where the device screens out the charge. So then they just fall on top of each other. Do the same thing once the counter ions from the polymer screen out all the charge effects. So I guess the interesting thing is that they match here, and they don't match down here. So the issue about polyelectrolyte concentration and how you do this stuff. So anyway, that's it for this. And we can look at papers on this, but basically I didn't this year. So it's hard to tell of what use it is in a sense. It's interesting to see how they've done this, but anyway, so this paper this week though is about this dynamic. I mean, they mentioned dynamic lights. They don't use dynamic light scattering, they use dynamic fluorescence spectroscopy and an optical microscope. So it's a little bit different. Basically, this is the basis. I'm going to go through some things on this. First off, the correlation function is something. So you want to describe systems like this. You know, we have some kind of, in particular, you want systems like this. This is from an extruder. You made a plastic bag, you put pigment in it, and then you get this thing. So you have A, B, C, D, E, F, whatever. I guess it's 2 E's. So like, which one is better? Like, how do you tell which one's better? Or you tweak the process and then you get like B. Is that an improvement over D? Like you can't tell by looking at it. One person will say yes, the other person will say no. So to get the answer, this is from Tadmore and Goga's polymer processing book from kind of the 70s, I guess, but it's a pretty good book to look at. It's got a lot of insightful things. Anyway, so he's going to use correlation function to deal with that. So he says, I'm going to take a position X, and get the average. So I'm going to average out like how gray it is. So I got a number for how gray. I'm going to take a position I, or position I prime and I double prime, and I'm going to take the difference between the mean and that. So it's a deviation. I'm going to multiply the deviations together. I'm going to sum over all the I's. So the I's are going to be like going across this thing like that, only the horizontal. It's a 1D correlation function. Then I'm going to divide by this S squared, which is like the mean squared, like the standard deviation. So it's the difference between the number and the mean squared summed and then normalized by the number, -1. That's the standard deviation. So we're going to normalize by the standard deviation and divide by n because it's n. Things he added together, I get a number from 0 to 1, this R of R, which is a correlation function. Just telling you how correlated the system is. If you want to know, so if you want to know the size, the scale of segregation, like how, which one is better. So this is a function of R, it's a function. So it's going to look like this, like it's some function R of R, and you're increasing the distance that you're looking at. So you tell some things about this is the size scale here, there's kind of a size scale down here. This is the width of one stripe, and this is kind of the distance between stripes, say, right? So you can kind of analyze the R of R curve if you want, but if you want to know how segregated, you integrate R of R and you get the scale of segregation, which is going to have units of R. So you can get the size, you get a parameter that you can say B is better than E by that number. If B is a smaller segregation number, then you're better off. In this case, there's also two features, the structural feature of the lines and the density of the lines, like how bright and dark. And Tadmore has another number for the bright and dark part of this thing. So anyway, so that's just showing, I guess the point of that is that this correlation function is all over the place. Like anytime you're looking at something you can't figure out and you want to quantify, you want a number that you have an error in the value, say that one's better than that one statistically. Like, and you can't tell by looking at it, then you got to go to this approach. So where you see this is if you have, this is just an example of that. So you have like a noise, it looks like a noise pattern, right? But basically, if you do this correlation, so that the autocorrelation function, so you're going to take like point here, point there, that distance, multiply them by each other, then vary that, then do that for all of these, and sum those and divide by n, then change the distance. Then you find out that this thing is actually, in terms of frequency, is a sine wave. Right, so you can have something that looks like noise and you can convert it to a sine wave. Right, so or it could be several sine waves. Right, so this is basically what an autocorrelation function gives you. It allows you to analyze the frequency dependence of the material. So you say, like, if I go a distance, I get a peak in correlation if I go a distance, whatever, 10. If I go 20 to 40, the things are correlated. See, that one and that one are correlated, that one and that one are correlated. So if you go 10 apart, they're correlated. If you go five apart, they're anti-correlated. So it should be, if you go like that far apart or something, that one would be here and one would be down there. Right, so you're getting this, even though it looks like a noise pattern, there's an inherent order to this thing that you can't see unless you do a correlation function of it. So that's the idea of this dynamic light scattering. You shoot a beam of light into a sample, and then you pick up at an angle. So the size scale you're measuring is the q 2 pi over the q value for that angle. And then you look at the light. So it's going to be a time correlation that you do. So you're measuring the sample. So that 2 pi over q gives you the size scale that you're kind of comparing. So you have stuff in the sample and they're moving around by KT. Like KT is just moving them around. Then you got to put on top of that some size scale R. That's our scattering vector. That's our thing like beam going out, theta, and then Q's equal to that, and Q is 4 pi, Q is 2 pi over D, the size scale D, or R, sorry. Right, so 2 pi, Q is 2 pi over R, so you got the size scale you're looking at. If you look at it, it's going to look a lot like this. It'll just be a noise pattern that you get. There's an example in here somewhere of a machine doing it. There, so this is what you get. That's the intensity at one Q value. You're looking at it as a function of time. So you can do a correlation function, like a certain distance apart, multiply them, and divide by n, divide by the whole thing by the average. You get the correlation function. And this is a log plot of correlation function. So something happens here at short times. And then there's a dramatic drop here that has some time associated with it. That's the relaxation time. for the system. That's like a characteristic time of the motion of the things that are in there, whatever they are, right? So this plot is kind of weird, like it's a log plot, so it doesn't really have meaning for the system, but it makes it kind of visible or something. So people use that plot. There's several plots that people use. They'll use just plot the correlation function versus time, and it's going to look like that. So that's an exponential decay. But it's not easy to see 37%. So when E you get 37% of the signal when you get to tau, 37 is 1 over E. 0.37 is 1 over E. E is 2.7 something. But 1 over that's 37%. So when your time equals tau, it's minus T over tau. It'll be minus 1, that's 1 over E, that's 37%. So when you reach tau, but you can't see any feature there, right? So because exponentially, you'd want to take a log of this. So if you plot log of the decay function versus time, you get a straight line, and then the slope is tau. The slope is going to be diffusion coefficient, which is 1 over tau. So that's an interesting way to plot it. You see, there's 4 ways to plot it. This one is the one that doesn't mean anything, which is the one I showed you. I mean, it shows kind of a shape, but it doesn't really mean anything. Then this is G2 versus log of time, which gives you this inflection point somehow from this. So I'm not exactly sure how that works. Basically, you can see the inflection point, and you can kind of pick out where the transition is. So anyway, what is this G thing? So, and there's also this homodyne measurement where you shoot the beam through and you collect here, and this heterodyne where you split the beam. So you can have a mirror that lets some pass through, some reflect. Goes to a normal mirror, goes over here, and then you combine the 2 waves here, and then you can calculate the correlation between the original wave and the scattered wave, and you can remove the noise with that heterodyne thing, but it's complicated. This one, the normal homodyne, is already complicated enough and probably good enough. So use Fick's law, and they figure out particles are moving around by kT, so they have a diffusion coefficient. This is all random Brownian motion description of how it behaves. Concentration fluctuations give rise to scattering. So you want to know the concentration as a function of time. You solve it and you get a Gaussian. We did that. That's basically the Einstein paper on Brownian motion we went through like early on. Right? So we have that Gaussian bell-shaped distribution. You put the particles in the middle and they're going to diffuse out away evenly and have a bell-shaped curve. Right, and kind of the standard deviation of that curve, or the variance of that curve, is going to be the diffusion coefficient. That's the idea, right? So mean squared displacement, that's the standard deviation, right? So and we know from Stokes-Einstein diffusion coefficients related to the hydrodynamic radius, because we have like the diffusion. It's driven by kT, and it's opposed by the friction factor, and by Stokes' law, the friction factor is 6 pi times the radius times the viscosity of the fluid. Like the bulk viscosity and the nanoscale radius, hydrodynamic radius, the drag coefficient radius. So anyway, so Stokes' law is a big part of this, and then this Fick's law thing that was, so both of those are in that first Einstein paper, right? Anyway, so you measure, so there's a bunch of G's here. There's capital G2, there's small G1, and there's small G2. All right, so that's one of the confusing parts of this thing. Like if they had just had one G, that would have been nice. Like this G is a very useful one because the exponential decay. That's the one you kind of want to see. So that's like 1 minus the G2 thing that you get. So capital G2 is what you measure. Intensity at some point, and then some other time averaged over all points. And then that can be written as an integral of the intensity at 2 times, and that fluctuating thing divided by T. T is the limits of the integral. So it's basically going to infinity. So it's this average of that intensity fluctuation. And then, so you sum up a bunch of those and you get this equation which relates to G1, but it has some constants. Like there's a B and an F constant, which you don't know, but you can get from the curve of G2. And then G1 is the thing you want because it gives you this gamma, which is the rate of decay, which is one over the relaxation time for the decay. Right. So it's a lot of stuff. You'll have to look at it. But if you look at this, you had the G2. So G2 behaves. So G2, when it goes to infinity. So this G1, so if time goes to infinity, it's e to the minus infinity is like 0. So that thing goes away. So when time goes to infinity, then G2 is B. So in measuring G2, if you wait long enough, you can get B. That's just where it's going to decay down to B. Right? And then, so B you can get from the data, and then you have this business. So you want to take the G2 infinity and divide by that, and then this equation. So if you divide this thing by G2 infinity, B goes away, and you have 1 plus F times G1T for that thing. So, and G2 is G2 is exactly that. So small G2 is exactly 1 plus F times G. So you want to get like F from this thing. So you subtract 1 from G2, and then you set T to 0, and then you find you have 1 plus F over here at 0. Like when T is 0, E to 0 is 1, and you have 1 plus F. So you can solve. So you have initial problem, you have like 2 unknowns in this thing, but you can solve both of them from the data. That's the bottom line. One's that intercept infinity, the other one's intercept at 0 plus 1. So once you have those, you can get the G1, which is the thing you wanted out of this data. So you can see people spent some time thinking about this. In the end, there's a machine that'll just spit out G1, and then you can just deal with it. So you can just get the diffusion coefficient, right? And the measurement's going to take about a minute. So it's like very rapid and very easy to do. It's basically monkeys could do this measurement. Right? You just stick it in, push the button, and it does it for you. There's one of these in the characterization center. The problem is, and like here's milk. Like you can put anything in it. Paint, milk, human body fluids, anything you can put into this, and it'll give you a size. So that's one of the drawbacks of it. It will always give you a size, and there'll always be some decay. So what that thing is that you're getting, hard to tell, but milk is supposed to be made up of these colloidal fat things that are surrounded by kind of a surfactant, and they're floating around. So apparently we did this in a lab class, and one person got a paper from Canada where they did a PhD dissertation on milk using DLS. So I think this data is actually taken from that PhD dissertation. I forget where, some Ontario or something. So anyway, skim 1% whole milk. Whole milk has bigger fat globules in it. Probably because there's more fat. I got it. Then it kind of is giving you this gives you a distribution function too of the thing. So you can, that's using this gamma. So there's a single relaxation time, or you can have gamma have multiple relaxation times. So you just be a sum of exponential decays. And from that kind of analysis, you can get this kind of population distribution from it. So you see, you can push this along like pretty far. Again, like another problem is that when you run this measurement, so what you're going to have is you need to have uniform temperature because KT is your driving force. So you stick your stuff in a tube into a bath of toluene. It kind of smells. There's a cap on it. Then the laser comes in and goes out, and you do your measurement. So anyway, if you have like a hair or some kind of dust inside the toluene and the vat, and there's like 5 liters, there's 3 liters of toluene, so it's a lot. And it all has to be microfiltered to get rid of anything. So on the size scale you'd be looking at with this machine, which is basically nanoscale, it's hard to filter that. There's not filters that work. Right, so there are a few details that are difficult to get at, but generally, like if you know your particle size and you don't have any dirt around that particle size, you can distinguish between the dirt and the particles that you're looking for, right? So anyway, so Rousseau, this is from this Paul Rousseau, who was at LSU. He was kind of a friend of mine, but anyway, he moved to Georgia Tech. He's kind of there now. I think he's retired now, but you can see like what aging does to people. Guy's like relatively young. Actually, he doesn't look that different, except that his hair is kind of not well kept here. But basically, that's what happened. So anyway, we got the four plots. So it's important to know when you glance at the results from this machine, like what you're getting, like which plot is it? Because if you look at it, like if you look at that curve I showed you before, wherever it is, it's just like, looks like, oh yeah, that's the decay time right there. You can see there's a decay time in it. But no, that's not the decay time. That's nothing. That's just like a feature of a log plot of an exponential decay. Kind of looks like that, but it isn't. So if you want to see that with a decay time, you need to see it shifted quite a bit when you look at it in terms of G2 versus log of T. So, and this one is the easiest one to interpret because it's a straight line. Right, so the slope is giving you the diffusion coefficient. Anyway, this one is the standard one that's nice to use because you can see an inflection point. You can observe like where you think the time is. So anyway, and then Stokes' law is used to get hydrodynamic radius from this thing. And then this is what Russo says. I copied this from he had a web page on DLS. If your object is a sphere, RH is R. For object is a spherical bubble, RH is R. If your object is a sphere on the outside but has inclusions of any shape inside, RH is R. If your object has some other shape, then like all bets are off. It's just RH is the equivalent shape of a sphere, equivalent size of a sphere that would have the same drag coefficient as the thing you're looking at, which means that like you don't know what it is. It could be like any, it depends on if it's asymmetric, it could be oriented, get different drag coefficients. And then if you're looking at a gel or something, because again, you can stick anything into this. It'll give you a size for gel. You put Jello into it, it'll give you a size. Like, what is that? You know? So you can imagine there's a lot of room for people to play around with this like thing. So yeah, that's just that's how you get the hydrodynamic radius from this thing. All right. Oh, and this is what it's actually measuring. So this is important. So this is when you shoot the beam through. So it's got to be a coherent beam, meaning coherent means that. Oops. So it's got to be collimated, coherent, and monochromatic. Coherent means that you have the waves, so they're all in phase with each other.
If you spend some time around the ocean, you may notice something kind of strange happens. The water level.
That looks interesting, but anyway, this is coherent, right? And monochromatic means you have one lambda in it. And collimated means that it's going in a straight line. In other words, divergent goes like that, and then focused goes like this, and collimated goes like that. Okay, so laser. Laser is a monochromatic, coherent, and collimated. Right. So when you say, people commonly say like as focused as a laser. Lasers aren't focused, they're collimated. If they're focused, it would be going down to a point, right? So anyway, so it's kind of a funny thing people say. So in order, when you have those conditions met, then you can get this speckle pattern. And what happens is you kind of, each spot is a scattering from kind of one particle and it's moving around by KT. If you get the correlation function for those things moving around, then you can do this, get this whole dynamic light scattering thing going. That said, there's two ways that people did this originally. Originally, they didn't do it that way with the speckles. Originally, they said there's a Doppler effect when light hits a colloidal particle because the wavelength of light is going to be like 0.6 micron, right? And then you can have particles that are moving around kind of on that range of size. That means that when the light comes in, it's a like wavelength 1, and when it goes out, it's a wavelength 2. If you can analyze that spectrum, you can get the velocity of the particles from it. Right? That's a dispersive, because you're dispersing the radiation when it comes out into different wavelengths. So that's what you do. That's what originally, when they had dynamic light scattering, that's what they did. But the resolution was lousy. And someone figured out how to do this correlation function thing, and then everyone went to this. So that technique's used for DLS, and it's used for X-ray photocorrelation spectroscopy, the speckle. And then if you go to neutrons, so you can kind of get monochromatic neutrons, you can't get collimated neutrons, and you can't get the other one, whatever that is. You can get monochromatic, can't get collimated. You can get collimated neutrons. You can get monochromatic, but you can't get coherent. You can't get coherent neutrons. You can't use this technique on neutrons. Neutrons are nice because you can tag with deuterium to see the material. So neutrons, when that came along, they went to this dispersive method, which was the original one for light scattering. So that all the neutron ones are like spin echo. They're looking at the wavelength coming out and seeing how this kind of Doppler effect for nanoscale structures and even molecules. They look at crystal motion with neutrons, crystal diffraction, and you can get the dynamics of the atoms in a crystal, or all the way up to polymers. So the neutrons are powerful for this dynamic. So anyway, so that's about it for this thing. This is the same thing. So yeah, next time I'll talk about this diffusive wave spectroscopy, which is there's a few things that are this microreology kind of grew out of this dynamic light scattering. So this whole idea of like putting beads in and watching them move around. So DLS led to XPCS and neutron elastic scattering, and also led to this whole other techniques, kind of like a rheology, using microparticles, kind of colloidal particles. So, oh yeah, we're out of time. So I'll go through that paper Friday, hopefully, if I'm still alive. Any questions or anything? We're over time, but